lightweight, fast, highly available. This is how serverless is often described. And it's all true, but making your solution reliable and performant depends also on you. Hi, I'm Swalek. I work as a software engineer in the Cloud Functions team at Google. And together with my colleague Marek, we will talk about ways to build solid production systems with Cloud Functions. Now, Cloud Functions is an event-driven serverless compute platform. Someone or something generates an event, and your code, your function, is executed as a result of it. This is pretty much the simplest way to run your code in the cloud. There are no servers to be provisioned, managed, patched, or updated. You pay only while your code runs. You can connect and extend multiple cloud services. And finally, Cloud Functions automatically scale, are highly available, and fault tolerant. But does it mean that all your potential problems with availability and performance are automatically resolved? The answer is not completely, as you can still apply multiple best practices to build a robust system. And we're going to talk about them in this talk. First, we'll cover reliability improvements. Then we'll move on to performance optimizations. And additionally, we will also discuss observability, which is important when you want to know what is going on with your system. Let's start with talking over reliability improvements through making your Cloud Function retryable and idempotent. We first need to realize that in distributed systems, failures happen. In fact, they are an inherent part of such systems, as it's practically impossible to build a solid production system or any complex system in which errors do not occur at all. The only way we can handle them is to make sure that we handle the errors gracefully. And Cloud Platform actually provides significant help in handling such errors. It is actually one of the big benefits of using cloud and serverless solutions. However, your software still needs to be prepared for error scenarios. If we think about who ensures reliability of your software running in the cloud, we realize that reliability must be a shared goal across Cloud Platform and your solution. When you use a Google Cloud service, Google takes care of its reliability. For example, when you call a Cloud Vision API, Google makes sure that the service is available and can handle your request. When you upload a file to cloud storage, Google makes sure it's persisted using replication under the hood. When you create your service in the cloud, Google still helps you build a robust system, but you are in control of its overall reliability. For example, your function may fail if it includes a bug. A call to your other service may also fail if that service returns an error or is flaky. How to ensure reliability of your Cloud Function? As we already know, functions are good for processing events. In particular, they're a great tool when connecting different services. For example, when processing the incoming data and uploading it to a storage system. In the success scenario, everything works. The data is processed and then persisted, for example, in a database. But what if an error occurs in this process? Your function may run out of memory, a network connectivity issue may happen, you may get an error response from the service on which you depend. All these issues may potentially result in data loss if the data doesn't make it to its destination. How to handle problems like this? Retries are an important strategy here. In a distributed system, it is normal that the services on which your function depend are not always 100% available. As a result, your function may fail occasionally. The simplest way to handle failures in serverless is to retry function executions. However, you should not force your users to retry requests to your system, but instead you should configure your system to perform retries automatically when needed. Cloud functions come in two distinct variants. HTTP functions are invoked by standard HTTP requests, which wait for HTTP response from the function. Background functions are invoked by events from the cloud, like messages on a Cloud Pub subtopic or changes in a cloud storage bucket. All functions are normally invoked once for an event, unless an error occurs. And here is where the two variants of cloud functions offer different execution guarantees. HTTP functions are executed at most once due to their synchronous nature. This means that the calls are not retried by cloud functions, and it is the caller who must handle any errors. And if you think about it, the caller should handle the errors anyway, as the request might not even reach Google's infrastructure. On the other hand, background functions are executed at least once, as asynchronous function executions triggered by events can be retried by cloud functions, as there is no caller who could do it otherwise. Let's look at some examples. This is an HTTP function which calls another service to upload payload from the HTTP requests. It simply sends a post request to that service. Easy, right? The problem is that the call to the other service may fail for whatever reason, for example, network connectivity issue. And this would result in the function failure, and if the function isn't retried, then the data may be dropped on the floor. In case of HTTP functions, the calls should be retried by the caller. So you can change your caller's code to either implement your own retry logic or use an existing library or module that can perform retries for you. For example, in this case, the promise retry module retries the calls to Cloud Function because we return the request promise inside the promise retry call. This is a simple background function. It also uploads data to another system. This time it extracts the contents from the Cloud Pub sub message payload. Similar problem here. If the dependent service fails, the function will fail because we return the promise as the function result. In case of background functions, retries should be configured on function deployment, either through Cloud SDK or Cloud Console, by enabling the retry on failure option. This way, your function will be retried until it succeeds. The first retry happens almost immediately after first function execution. The next retries follow the exponential backoff policy, capped at 10 seconds, and they happen for up to 7 days if your function keeps failing. However, you should be careful with using this option because it will retry your function on any error. Also, if it is caused by a bug or some unexpected input data. So if you use this option, you should return errors from your function only on transient issues and preferably handle the permanent problems inside the functions completely. So in general, there are multiple places to apply retries. As we saw, you can retry calls to an HTTP function. You can configure retries of a background functions. You can also retry calls to dependent systems from inside the function. For example, by configuring the client libraries that you use. You can search for what options they offer. or you can write custom code. And finally, as already mentioned, persistent errors should be distinguished from transient failures, and retries should be applied only on the latter ones. Let's look at a bit more complex example now. Here's a function which processes the data and writes it to two storage systems. First to the upper one and then to the lower one. The problem is, as you may expect, that any of the uploads may fail. For example, let's assume that the upload to the second storage failed. Well, in this case, the data would not be saved in the storage, but we know how to handle this, right? Apply retries. But are retries always safe? For example, here, if we apply retries, the second function execution will result in storing the data in the second storage, assuming that the upload succeeds this time. However, the first storage will receive a duplicate because the upload to the first storage will be retried. And duplicates introduce inconsistencies, they are not good, so we don't want them. Can we do anything to prepare the function for retried executions to avoid issues like data duplication? The answer is yes, and the concept of idempotency comes in handy here. A function is considered idempotent if an event results in the desired outcome and side effects, even if the function is invoked multiple times for the same event. So making a function idempotent is actually required to make it behave correctly on retried execution attempts. Let's look at a non-idempotent function first. This function uploads the received contents to Firestore first, and then it uploads the same contents to another service by sending a post request. One potential problem here is that if the upload to the Firestore succeeds and the upload to the other service fails and the function is retried, another document with the same contents will be added to Firestore. So we'll have a duplicate, which can also be seen in the Firestore database viewer. But this may also happen if the Firestore was replaced with another system. And as we know, we don't want duplicates. They may introduce further inconsistencies. They may cause accounting problems. The users may be confused. They're not good. To solve this problem, we'll use Event ID. This is a number which uniquely identifies each event. And what is important here is that even if the function execution is retried for the same event, the event ID itself remains unchanged. How do we use it in our code? We first extract the event ID from the event context, and then we use it as the Firestore document ID. This way, if the function is retried, it will not add a duplicate object to Firestore, a duplicate document. Instead, it will overwrite the existing document, which exists under the same event ID, with the same contents anyway. Similarly, some other systems also support so-called idempotency keys. And if the system that you use supports them, you can use event ID as the idempotency key. As a result, we no longer observe duplicates in the Firestore, and similarly, we wouldn't observe duplicates in other systems to which we passed event ID as the idempotency key. But what if the system on which we depend does not support idempotency? Here's an example. This is a function which uses SendGrid, the email delivery service, to send an email from the function. The problem is that the send call is not idempotent. What can we do about it? We can record event IDs. This is the general approach here. we use a database like Firestore in this example, but other database could work as well, to store the already handled event IDs. And then, when the requests come, before we enter the non-idempotent section of the code, so the one which sends an email, and if it was retried, it could result in duplicate emails being sent. In this section, we first check by querying Firestore whether the event was handled. And if it was not, we execute the non-idempotent section and then store the event ID as handled in the Firestore database. This way, the chance of unwanted retry calls to the other service of the duplicate emails being sent are greatly reduced. However, there is still a small chance that if the function attempts are executed concurrently, a duplicate email may still be sent. To practically resolve this issue, we can use the lease mechanism. It allows us to get an exclusive access to the non-idempotent section of the code for the specific amount of time. In this example, the first attempt gets the lease before it enters the critical section, the one that sends the email. The second attempt, which happens while the lease is taken, is actually rejected because it cannot get the lease. And finally, the third attempt, which happens after the first attempt failed, takes the lease again and eventually succeeds with handling the event. How do we apply this approach to our code? We use a Firestore transaction. And this time, it not only checks whether the given event has been handled, but it also saves the timestamp until which the current function execution has exclusive access to the critical section, again, the one which sends the email. If another request comes before this timestamp, I mean another retry of the same function, it will be rejected, so no concurrent code execution will happen. And with this approach applied, we practically eliminated the unwanted retries. So to summarize, there are multiple ways to make your function idempotent. You can ensure that your mutations can happen more than once without changing the outcome. You can record which event IDs have already been processed. You can query database state in the transaction before mutating the state. You can also supply idempotency keys when calling APIs which support them. And finally, you can also clean up duplicates out of band through an offline process if that approach is fine in your workflow. All right, so to see retries and idempotency in action, I will demonstrate a sample order processing system for my fake restaurant called Kale Pizza. How does it look like? Going from the left side of the diagram, there is a website through which customers can create orders. The website invokes one Cloud function, which publishes a message to Cloud PubSub topic. Then there is another function which is triggered on messages from this topic, and it does three things. First, it calls another service represented by another function, which chooses the cook who's going to handle the given order. Then it stores the order together with the selected cook in the Firestore database. And then it calls yet another service, yet another function, which triggers meal preparation. And finally, the restaurant has a website which simply syncs with the Firestore database to view the incoming orders. All right, so let's see this in action. OK, so I'll click Start right away. And here we have these two websites. So one is the client-side website, and the other one is the restaurant-side website. So the one on the left generates the event. I'm generating them every second here to see more of these events going out to make it more interesting. And let's see what we get here. So far, so good. All the retries are going through. Okay, let's wait a bit more. All right, let's stop it. So what do we see now? 44 orders went out and only 41 orders came in. So some orders got lost here, and I can see that, for example, the first one here, right? It didn't make it to the restaurant. It didn't make it through the whole pipeline. So something is wrong here, and lost orders means unhappy customers, not good for your business. So let's investigate what happened. So I have the functions deployed in my project, and the main function, the one which performs those 3 actions, is the process order function. And like I show on the diagram, it does 3 things. It calls the choose_cook service, then it stores the order in the database, and then it calls yet another service. So probably something failed here. So let's see. And here is where the observability tools in Google Cloud Platforms are in Google Cloud Platform are useful. First, I can see that on the executions chart, there are some errors indeed, right? Most requests were okay, but there are also some errors. And if I scroll down, I can see the errors from the last 7 days. And if I click here, I go to Stackdriver error reporting, in which I can see the errors chart. I can see a sample stack trace. And finally, I can see some logs. Okay, let's go to this one or this one. I can click view logs and see the logs here. All right, so if I filter only by this execution ID, I can see a sample function invocation. So the function execution started, received an order, but then it got the transient failure from the choose_cook service. And if we look at the implementation of the choose_cook function, we can see that it's implemented in a way that only succeeds 90% of the time. For the remaining 10%, it fails. Of course, this is a synthetic example of a failing service, but as I said, you should assume that the function that you are calling or the service that you are calling may fail for many reasons. And similar story about the other function, prepare meal. It also has the success ratio of 90% only. All right, so we know what happened, and we know how to handle transient issues, right? We can apply retries. So I have the second version of this function here, process order retry, with the same source code. It does the same things, but it has the retry on failure option enabled. I use this option when deploying the function. So let's see how this one works. Let's switch to the topic, Cloud Pub subtopic and Firestore collection, which actually are operated on by this second version of the function. All right, so I've got orders going out, orders coming in. By the way, the colors are just color-encoded event IDs so that we can visually compare the right and left side and see the differences. Okay, I can stop. And what do I see? 26 orders went out and 30 orders came in. So this, okay, 31 orders came in. So definitely more than I sent. So there must be some duplicates, and I can already see some here, which appears even 3 times the same order, the same event IDs with 3 different cooks assigned. So they may start preparing the meal right away. Well, the customer may be happy with the extra 2 meals, but still, that's not good for your business. So what can we do to avoid these duplicates? And the answer is introduce idempotency. So I have the third version of the function here. And this time I modified the source code. And the piece that I modified is the one which runs, which stores the order in Firestore. So I introduced a transaction which first checks whether the given event ID, whether the document with the given event ID, or in this case, the order ID, was already processed, and only added to the. I only added to Firestore if it was not, if it does not exist yet. This way, I also prevent the issue of overriding the same order with a different cook assigned. So let's see how this one works. So I have the third version here. Let's start generating the events. All right, it takes some time to process them. We should start seeing them here. All right, they're coming in. Let's wait a bit more to see if we get the desired result. So far, so good. Orders catching up. Yep. Okay, so 29 orders generated, 29 orders came in, so no lost orders and no duplicates. And I'd like to highlight that I didn't touch the services that were flaky, that fail for 10% of the time, but instead I reconfigured the other parts of the system to handle this situation in a good way. Moving on, I'd like to summarize the first part of the talk, saying that you should introduce retries and make your function idempotent to improve reliability of your functions. Thank you, and with this, I would like to introduce my colleague Marek, who is going to cover the second part of the talk about performance optimizations.
Thank you, Swalek. Thank you. I'm very happy to be here with you. I wonder how many of you actually use Cloud Functions or have tried Cloud Functions. OK, so this is going to be a little bit, it's not the basic topic, so I assume that all of you know what the call start is. So I assume that all of you know that the call start is when the infrastructure spins up a new instance that will execute the code of your function. And you probably know that this happens if there's no instance that is serving the traffic, or maybe that there is a sudden surge in the number of requests that your function has to handle. And then there must be many instances executing at the same time. You've probably heard that functions are stateless. And that's because there are so many instances that came in and come out. And that's true, but the fact is that they are not always stateless, which means that if there is an instance that is serving, it's probably going to be reused for future invocations, for subsequent calls. And this lets you reuse the state that the instance has to improve performance. And I will show you in a little bit how you can do that. So the first example is connections. Let's assume that your function has to connect to some external system, and you can improve performance by maintaining persistent connections. So you establish the connection at the first function invocation in the instance that is serving, and then subsequent calls that will hit the same instance are going to have the connection established. So this may not be so important if the system that you connect to is in the same data center or very close, but it's very important if the system that you are connecting to is on the other side of the world. And then the connection establishment actually takes time. A small caveat here is that you have to be careful with the target system that you are connecting to, because it may have a limit on the number of connections that it can handle. And if you use persistent connections, any instance of the function that is actually out there serving will maintain the connection. So it may exhaust the connection pool of the target system. Going further, the same principle may apply to API objects. And such API objects very often have connections inside somewhere. So it's very useful to declare those API objects on the global scope in the code so that the connection is not re-established every time you create the API object. Similarly, if there is a global variable that gets recomputed every time your function is called, it's useful to put it into the global scope so that it's computed once and then reused on subsequent invocations. But on the other hand, it's not always true that it's better to perform those computations in the global scope when on the cold start, because it may happen that the value is not even used. So if you use the value under very rare conditions, it's better to compute it lazily and not in the cold start, because the best optimization is when you just remove the code that is not used. And this is especially important if your function, if you declare several functions in the same file, which you can do. And actually many people, everyone that uses Firebase probably did that, because this is the common way how Firebase functions are written. And if you do that, you have to know that every function runs in a separate set of instances. So if an instance handles the execution invocations of the first function, it will never be called to execute the second function, because that's a separate set of instances. So if you initialize a very heavy variable that is used in the second function in the global scope, it's just a waste of time. And that also applies to those require statements in Node.js, where you include libraries that you are going to use. So it's a bit awkward to require libraries inside the function, but if you declare multiple functions in the same file, that's a performance optimization. When you apply this kind of optimizations, please be mindful that the function runs only until the callback is called. If you try to execute something after it's called, there will be no CPU actually to do that, and the code will not progress. So it may be tempting to write the code like this, to send the result to the customer, to the user, and then do some computations to optimize for subsequent invocations. But don't do that, it will not work. I've told you about caching some computations inside functions in the global scope inside Node.js process, but you can use also a local file system where you can write files. And those files will survive on this particular instance as long as the instance is alive and is serving. But you have to be careful here, because the file system is in memory. So it's not infinite. And every file that you write is going to consume the memory, the runtime memory of your function. So eventually, if on every invocation you create a new file and you forget to delete them, you will run out of memory. And when you run out of memory, your instance will die. And this means that there will be a cold start for future invocations. And of course, when there is a cold start, you lose the state that you carefully prepared inside this instance to optimize for subsequent invocations. So it's better to avoid them. And you can avoid them by taking care of not exceeding the allocated memory, not throwing any uncaught exceptions, just catch those exceptions. Because sometimes the process that executes the code may actually crash. That also causes a cold start. And when your function times out, also the instance is put down and another one is started. This all was about caching computations inside the instance that executes your code. And this cache, this state, is available only for this particular instance. So you have to recompute it in every other instances. It's also possible to go a little bit further to share some state across all the instances. But for that, you need to use some database, for instance, a serverless database like Firestore. So the summary for this part of the talk is that you can leverage the state of instances to speed up subsequent invocations. And I'm going to show you an example how I managed to optimize a little bit of my application to just serve faster. And the application that I prepared is converting text to images. So it's applying caption on a picture. And the parameters to the functions are just two, that caption to be written and whether we want some background or not. And we have very awkward users that most often they don't want any background, they just prefer white picture. And we are going to optimize for this use case. So what the function does is first it fetches the background from cloud storage, then it applies the caption using image magic, and finally it uploads the result also to cloud storage. The code is simple, exactly as you would probably imagine. So create a temporary directory, download the background file, load the file into memory, draw the caption, write the file to disk, and upload it to cloud storage. Very simple, right? And when we debug our distributed application, where we analyze what happens in such an application, it's very, we just have to use the platform tools to observe what's going on. So we are going to use cloud logging and monitoring to see either logs from individual invocations or plots of some patterns that are in our system. Swalek already mentioned error reporting, when you can see errors grouped by error types and you can directly go to logs. And in the context of monitoring, you can also set up alerts on certain thresholds of metrics and other conditions. And so the first thing that we do is we deploy our function and test it at scale. In our case, the scale will be just 5 QPS for 5 minutes. But yeah, I think that's enough for testing. And when we start that, we soon realize that we have quite a lot of errors. It's about 5%. And when we look at the plot of memory usage, we see that the memory actually goes quite high. It reaches the limit of 256 megabytes that we allocated to the function. So probably we misconfigured our instances. We just gave them too little memory, and image processing requires the memory to load the image. So probably we just need to improve on that. But let's first check whether this is indeed the case, that the errors were because of memory ran out. So let's go to the function page and let's view logs. When we filter the logs by error type, we immediately see that those errors were memory exceeded errors. So of course, we add more memory. We redeploy the instance with a larger amount of memory, and we test it again. And what happens? Luckily, the errors went down to 2%, but they are not completely gone. It's still something's still wrong. And we see that the memory usage actually went up. In the second test, it went up even up to 500 megabytes, which is allocated. So it looks like we have a memory leak. And I will let you look at the code, and maybe somebody can find where the memory leak is. Does anybody see the error here? OK, one person sees an error. Let's see if others see it. Second one. OK, very good. OK. So some of you already know that the problem is that we create a temporary file, and we don't delete it at the end. So the temporary file is created here. We just generate a random string for the file that we are going to generate. And we just generate it, we write it to disk, and we never delete it. So this works as I described it the first part, that whenever you write something to your local storage, it's consuming your memory. So it's very easy to fix. We actually just need to delete the file because before we finish the function, and that's the fix that we applied. And with this memory leak fixed, we immediately see that firstly, we don't have any 500s, no errors. And also the memory usage went down even below this 256 limit that we applied before. So the question is, shall we now reduce the amount of memory for the function or not? But let's take a look at the performance. We see that with more memory, our function actually runs faster. And that's because this is how we allocate CPU to functions. The more memory the function has, the more CPU it also gets. And giving twice more memory gives also twice more CPU, so your function runs faster. And in our case, we would like to have the system quite performant, so 2 seconds of latency is probably quite good, but 4 seconds it's a lot too much. So let's stick to this instance size and this amount of CPU in further work. So now, let's take a closer look where the function actually spends time on, what's the most costly part. So we go to cloud logging, we select an individual invocation, we click on it, and then we can filter logs from just one invocation. And you can see that the majority of time is spent on uploading the file to cloud storage. That's quite surprising. Google has good network. Why would that be so slow? And the fact is that we actually used very bad compression type. And by the way, this is not a very good idea to look at one individual invocation to analyze what's going on in distributed applications, because this may be just some random problems here, and maybe in other cases everything will work fine. So it's much better to report custom metrics to Stackdriver, for instance, and look at the behavior at scale. But in our case, logs gave us this information. So the problem with uploading to cloud storage was that the files were big. We use BMP file images, which were about 7 megabytes, while PNG took only 10 kilobytes. So the first optimization that we can apply is to switch the compression from BMP to PNG. Very simple. And by the way, also this uploading speed depends on the instance size, because uploading data requires a little bit of the CPU. So you can also improve on that by giving the instance more memory and more CPU. So when we change the compression type, our function runs faster, almost twice, much better. Can we do better? Of course. I mentioned that our users are a bit weird, that they don't like backgrounds, they like black and white. So we don't really have to download the background image on every invocation. Let's just not do that. And this is actually the case that I tested, without any background, just black and white. So we can now download the background only when it's needed, and we can download it only once. And with this optimization, we save another 50 milliseconds. And some of you may have noticed that on some previous slides, it was 90 milliseconds or 80 for this phase, for downloading the background. And this is what I mentioned, that one individual invocation will not give you precise data. You need to have multiple invocations, so that's why metrics are always better than individual logs from one invocation. So now, we can also, I mentioned that it's useful to move computations that are that can be done just once to global scope. So in the next step, I moved creating of the temporary directory into the global scope and creating the GCS bucket object, which is this, we always use the same bucket for uploading the image and also for downloading the background. So we can just move those two lines into the global scope, and that will save you another 25 milliseconds. Not so much, but still significant maybe. More happy users. So to summarize what we did here, firstly we fixed the memory leak in our application. We increased the instance size to give it more CPU. We used better compression so that we don't spend so much CPU time on uploading images to cloud storage. We lazy downloaded the background image because it wasn't used in all invocations. And finally, we moved some computations to the global scope so that it's performed only once. And while doing that, we used the platform tools to observe our systems. We use logging, used monitoring. Maybe we didn't use logging in the best way. We could have used more monitoring. And that's about that, but we still have time to answer your questions.